But imagine a world where we could develop better battery materials that can store more energy, or where we can develop better catalysts that are very hard to simulate today with classical computers to, for example, remove pollution, or better organic LEDs, your TVs at home would be much brighter, for example. That is where quantum mechanics excels. We are at the beginning. We don't know yet what else will come.
Du lytter til Fremtidens Kapital. En podcast, der undersøger, hvordan kapital i innovation og vækst er med til at forme fremtiden. For kapital handler om mere end afkast. Den handler om at skabe udvikling, drive forandring og sætte retningen for, hvor vi bevæger os hen, lokalt og globalt. Denne podcast er produceret af Mazanti-Andersen advokatpartnerselskab. Vi har et af Danmarks største teams dedikeret til rådgivning af kapitalforvaltere og investorer. I denne serie møder vi en række aktører, der hver især arbejder for et stærkere og mere innovativt Danmark. Vi møder dem, der tør satse, skabe og forme fremtiden, og dem, der på hver deres måde sætter sit præg på fremtidens kapital.
What is quantum technology? Why is it suddenly showing up in conversations when we talk about innovation, national competitiveness, and long-term investment? And what has actually changed to move quantum from theory towards real companies and real products? I'm Thomas Weisberg, partner at Mazanti-Andersen law firm. To help us explore the world of quantum technology, I'm excited to welcome our guests. Joining me in the studio are two practitioners who work at the intersection of physics, technology, and business. It's Helmut Katzgraber, is Chief Science Officer and General Partner at 55 North, a Danish-based quantum technology fund, and Kurt Stokbro, the CEO of Danish-based Sparrow Quantum. Welcome.
Thank you,
Thank
Thomas.
you.
Kurt, let me start with you. Could you briefly introduce yourself, your background, and your current role in Sparrow Quantum?
Yeah, I'm a quantum physicist. I come from Jutland, so I did my undergraduates in Jutland in Aarhus University. However, when I wanted to do my master's, I saw this new things called neural networks, which I then went to the Niels Bohr Institute to do a master in that. And actually, this is the kind of theories that got the Nobel Prize last year and is the foundation of all the AI. However, when pursuing a PhD, I wanted to do some real physics. So I went to the Technical University and studied quantum theory of materials. And that became my academic career. I had a research group where we developed software for simulating electrical properties of materials. And at that time, I saw that transistors, they were getting smaller and smaller. So the kind of classical methods that were used to simulate them didn't work anymore. So they needed some quantum theory in the semiconductor industry. So I made my first spin-out, Atomistics, back in 2003. And we developed software for the semiconductor industry. It ended up with me leaving the company, and shortly after it went bankrupt. So that was an opportunity for me to try once more. I've learned a lot in this with Atomistics, and I assembled a team of some of the best guys from Atomistics, and we started QuantumWise. So actually, quite quickly, we built up some software. We got into the semiconductor industry, and we just grew organically and became the market leader for atomic scale modeling in the semiconductor industry. And today, I mean, all semiconductor companies are using our software today. So it was a big success. And I sold the company in 2017 to Synopsys, who is the market leader in this space of EDA software for the semiconductor industry. And then the question was, what should I do now? And I decided to become a tech investor. And I saw this new space called quantum, which I thought was really interesting. And I became an early investor in the company Sparrow Quantum. However, it was not really going anywhere. And then the founder, Peter, asked if I could take a more active role. So I became the CEO in 2022. And together with Peter, we made a new strategy. And then things evolved. And today we 45 employees in Sparrow just closed the biggest investment round here in the Scandinavia, 27.5 million euros. And things are just evolving really quickly now. Peter got a big prize. They hired the entire opera to celebrate Peter and his technology.
Fantastic. We'll come back to the Sparrow technology later on in this segment. Thank you very much. And Helmut, how about you? A brief introduction and what led you into the world of quantum technology?
So my background has one constant, and that is change. I've lived in different parts of the world, grew up in South America, studied in Switzerland, originally theoretical physics. And because I didn't know how to program, I decided to do a PhD in computational physics, which is basically get thrown in the water and start swimming. And over the course of my academic career, eventually became professor with a focus on algorithm development, on very hard optimization problems in materials. And this was roughly the time where quantum technology started to come. And so it became natural that I started benchmarking these systems, trying to understand them better, simulating them. This eventually led to Microsoft make me an offer that was hard to say no to. So I left the university, went to Microsoft for 2 years, led the team that built the first beta of what is now known as Azure Quantum. It was at that time the first cloud-based quantum computing service where quantum devices are housed. And after 2 years, I switched to Amazon and led the, at that time called Quantum Solutions Lab, which is a team of interdisciplinary scientists whose focus is to look at real-world problems, for example, Amazon's logistics or optimization of robot motion or clinical trials, peptide folding, all across verticals, and see where quantum technologies could have an impact in the future. And that gave me a very broad overview of what quantum devices can and cannot do. In parallel, I started helping out with due diligence for venture capital funds. And when I received the phone call, how would you feel about living in Denmark? I signed up, and here I am today.
Thank you very much. So I think it's fair to say that we really have some expertise around this field with us in the studio today. Quantum technology can be a difficult field to approach from the outside. It's based on physical principles that challenge our everyday intuition and differ fundamentally from classical technology, to the extent that even Einstein famously struggled with some of their implications. So, to set the scene before we dive into the technology, could you shed some light on what exactly quantum physics really is?
I think we all know what classical physics is. If you kick a ball, the ball will have a trajectory, will land at a particular spot. And we have very good mathematical equations and algorithms that describe this very deterministic behavior. Quantum physics is the physics of the very small, the tiny, tiny things like atoms, molecules. And what we learned is that the physics that we use to describe everyday phenomena just does not work anymore at these small length scales. And so in the realm of quantum physics, you start getting very odd effects. For example, particles can behave like waves, in particular scenarios, while in classical physics, energy can have any value. So for example, if you start pedaling harder and harder on your bicycle, you start going faster and faster. But in a quantum system, that's not the case. You can only have very discrete energy levels. So imagine pedaling, and then you jump from first gear to second gear to third gear. So it's a quantized world, hence the name. And so everything is different. And more importantly, we cannot really speak anymore about particles versus waves. It's a blur, and this is why you describe quantum system with probabilities. And so the way that we very deterministically know exactly where a ball will land if we kick it, in a quantum system, we can merely give a probability. And if we now go and check where this, say, electron or atom is, then we do what we call collapse the wave function. We measure, we destroy the quantum state, and we either find it in a particular state. So it is a very different, weird, fragile world that allows for some phenomena that are not in our everyday language or experience, and that lead to some special things that most of you might have heard of, which is superposition and entanglement. For example, a quantum state can be in more than one state or a quantum system can be in more than one state at the same time. and two or more quantum systems can share the same state at a distance. And so these effects that we really need to understand the physics of the very small are the foundation, for example, of new types of devices that are being built today, either for telecommunication, for sensing, or for computing.
Maybe if I can try to come with some examples. So let's say, in the classical world, you can have a ball or an object that can be either black or white. But in quantum, actually, you can be black and white at the same time. So you can have one particle that have two properties at the same time. But if you try to test it for the property, then you'll find out it's either white or black, but you cannot know before the measurement the outcome of the measurement, whatever it's white or black. There's two probabilities to it. So this is what we call superposition, which is an essential part of quantum technology.
But it is correct to say that it's not because that we don't know, it's because it really is in all positions at the same time.
Yeah. So it's both black and white at the same time, and there's this other concept, entanglement, which is actually a little similar to the superposition. It just means that if you have several particles, then they can also be, let's say, that all the particles are either black or white, so they can share a superposition, many particles. And here comes the quite interesting thing. So now let's take, you have 5 particles and they are either black or white. So now if you measure on one of the particles and find out that this particle is black, then automatically all the others also collapse into a black state. And that's independent of where they are positioned. I mean, they could be positioned at a star light where away from us. I mean, because they share this common wave function, it collapses when you just measure on one of them.
So distance does not make any difference in this scenario. It can basically, as you said, be at the other side of the universe because it's for some real reason is one system.
If I may add, there is this very famous thought experiment called Schrödinger's cat, where basically, I'm pretty sure most people have heard of that in one way or the other. But basically, you have a cat inside a box with a radioactive source connected to a little vial with poison. And so the radiation is a stochastic, a random process. It might or might not emit a particle. And so while the box is closed and you cannot look inside, the cat is in a superposition between alive and dead, because you don't know if the poison has been opened or not. Even worse, if you were able to entangle that box with other boxes with cats, and you were to open that one box and find the cat to be dead, you would have committed mass murder and killed all the cats at once. So that's superposition and entanglement.
We often discuss these things and think, I mean, it's weird, but I mean, the world is weird. I mean, think about, we believe that classical physics is rational and that apple falls down a tree, that's a rational thing. But I mean, thinking about it, what's really happening is that the entire Earth is connected with this apple, and the entire Earth is actually putting a force onto this apple. Isn't that strange? I mean, so...
Yeah, you're still struggling with gravity. What is it? It is really.
Yeah.
So, and the point I think here is that it's not just theory; it's how it actually is.
Yes, these are measurable effects.
Yeah, it's measurable because it has been around for many years, and as I've read somewhere that even Einstein, he was in discussions with Niels Bohr, where the sparrow is. Has deep roots in that institute, Niels Bohr Institute, where he famously said that God does not play dice because it's all boils down to probabilities, as you said.
Yeah, Einstein tried to make a lot of thought experiments on why quantum theory could not work and tried to find some faults in quantum mechanics. So they had a lot of discussions, but Bohr could always find a solution. So in the end, Einstein gave up. I mean, so.
And the next step, of course, is turning to the application of this, because, as you said, that Einstein, 120 years back, they were talking about quantum physics, but now we are beginning to actually utilize or actually control to some extent some of the craziness that you talk about.
Yeah. So when we talk about quantum technology, we talk about version 1.0. I mean, this is all the electronics. I mean, all electronics use quantum theory, else it would not be working. But it doesn't explore quantum theory. So this is what we call quantum technology 2.0, and this is what's happening today. And this is where we start to really put matter in the quantum state and keep it in the quantum state and let it evolve in a quantum state. And the effect of that is what we then are using into new type of devices. And that can be new type of sensing devices with a very high sensitivity that cannot be achieved outside the quantum state. It's quantum communication, where you use that if you tried to measure a quantum state, you destroy it. So if somebody is listening into a communication, you will be able to see it as a receiver, that there's that there's a listener. And the last thing is quantum computing, where we keep matter in the quantum state, let it evolve. And this cannot be simulated by a classical computer because there are so many different outcomes, exponential outcomes as a function of the size of the system. And this allows to solve problems that are unsolvable on classical computers.
So if I may add to this, I think it's fair to say that wave one had quantum effects. So for example, lasers, transistors, or MRI machines for medical imaging. And in wave two, we're actually explicitly using these quantum effects to do things. It's not just a feature that happens to be there, but it is actually what we're trying to control, manipulate to be able to do things.
Yeah. Mm. I think we'll come back to the three applications that you just mentioned, computer, sensing, and communication. But at least for laymen like me, I think the computer is something that we read about in the news, and hear that Google has made this processor, quantum processor, etc. Could you try to? I think many of us have seen the imitation game with the Turing machine, which was, to my understanding, the most basic computer you can think of, which has been built on to make the computers, the classical, traditional computers that we know today. Could you try to compare a traditional computer and the development in a traditional computer to what is a quantum computer?
I mean, a classical computer uses bits. So a bit is something like 0 or 1. And then it manipulates these bits. In a quantum computer, you use these quantum principles of superpositions and entanglement. So you no longer have bits, you have so-called qubits. So these are superpositions of 0 and 1s. And when you have 2 qubits, then they can be entangled. And that makes the phase space that you explore exponential in the number of qubits. So if you have 2 qubits, you have 4 possible states, 3, 8, 4, 16, and so on. So once you get to 50 qubits, then you have so many states that you can no longer simulate it on any classical computer. And this is the kind of principle you are exploring, because there's a lot of problems that a classical computer cannot solve. For instance, simulating atoms or molecules, you need to explore quantum mechanics, and this kind of exponential number of states are present, and a classical computer cannot handle it, but you can handle it on a quantum computer. So this is one of the applications we're thinking about.
I think the compute unit on a classical computer is a bit. It can be 0 and 1. And to be able to do a calculation, you need logical gates. They're usually ands, ors, XORs, what you typically find. And so if you take computer code that you would write today, for example, to sum up numbers, that gets converted down to a very basic level set of instructions that are, ands and ors and so on. In a quantum computer, you have these qubits. Now, a nice pictorial way to represent a classical bit versus a qubit is to take something that physicists call the Bloch sphere. So imagine a football that is hollow on the inside. Then a classical computer would only represent the north and the south pole, +1, -1, or 0 and 1. A quantum bit can have all the states on the surface of this ball. So you see already that the compute space by itself is infinitely larger. But not only that, you have, in addition to the ands and the ors, more of these logical operators. You have entanglers, you have things like Hadamard gates, so you not only do you have the variables by themselves are richer, but also the set of gate operations you can do is also expanded. And that gives you abilities to compute certain things that classically are very, very difficult. And as Kurt said, the footprint of these states for a quantum system grows exponentially. So it is less the CPU, it is more storing these states that becomes unsurmountable. At some point, there's not enough storage on this planet to be able to store, for example, a simple molecule with 100 atoms. That would be impossible. You would need a computer that basically uses every single atom on the universe as storage.
If you have all these possibilities with the ball, where it could be everywhere, as I understood it, once you need to get some kind of measurement out of it.
Yes, and that is when you project it. You see, you are somewhere on the sphere, and then when you look at it, bonk, it just chooses one point, and this is where the result comes out.
And that is the right one, because I can basically also say that I know everything in the world, and once you give me a question, I'll just spit out a reply.
Well, the right one is a delicate statement because it's probabilistic. It might be the right one.
Yeah. So it's basically probabilistic.
Yes.
Yeah.
I like to go back to one thing that you just mentioned in passing, and that is this machines that were used to decrypt the Enigma, the German codes. There's another beautiful parallel between classical computers and quantum computers. And that is that when you look at the history of computers, we always started building a machine that can do one thing. We had a really hard mathematical problem that was very tedious to solve. In the case of Enigma, it was cracking those German codes from these machines. When you think about quantum computers and why governments were initially interested, it's because, as we'll probably talk about later, we can very effectively crack current encryption schemes on these machines. So the original focus was, maybe we can use this to find out the secrets from other countries, for example. It started with a single application, and then it became what we call a universal device. And so when you look at, again, those mechanical machines, electromechanical machines that were used to crack Enigma, eventually they resulted in machines made out of vacuum tubes at Los Alamos National Lab, first to simulate neutrons for atomic reactions. And then eventually we became to the silicon-based transistors, where we then realized, we can use this for so many other things. And this is why today we can hold a phone in the hand that can do pretty much anything. We are a little bit just at the brink going from these special purpose machines that originally were built for one thing only to the point where we want to be able to program them and really discover new things by just writing code the same way that we write classical code and execute it on a laptop. So it always started with analog technologies that eventually became digital. Analog was for a particular purpose, and eventually it became something programmable that allows us to really be creative and explore nature.
And that also, ties into what I've heard, that one of the biggest problems with quantum computers, you mentioned the single purpose, but it is actually to figure out what can we use it for.
let me talk about some of the applications of compute, and I think Kurt might be best to talk about all applications in sensing, for example, or networking. I think the easiest way to characterize a quantum computer and say, well, where does it work? When you're trying to understand a quantum mechanical system. You see, classical computers struggle with that because of this exploding phase space and the memory requirements. Quantum computers don't. And so if you want to know, well, what can I use a quantum computer for? It's to understand quantum mechanics. Now you might say, well, it's this tiny stuff. Why should I care about that? It's simple, because if you want to develop a new drug, you need to do quantum mechanical simulations. If you want to develop new materials, you need to do quantum mechanical simulations. And so anywhere where quantum reigns supreme is where these machines work best. Now you might say, well, isn't that a very narrow scope? In the bigger scheme of things, yes. But imagine a world where we could develop better battery materials that can store more energy, or where we can develop better catalysts that are very hard to simulate today with classical computers to, for example, remove pollution. So that is where quantum mechanics excels. And there's many applications, in pharma, in material science, where it will have a huge impact. And, we are at the beginning. We don't know yet what else will come. We do know, however, that there are some applications that will be very cumbersome on quantum computers. And one of them, for example, being logistics. If you read in the press, everybody says, oh, yes, we will solve logistics. It will be very hard. Once you take a real-world optimization problem from logistics, you will soon understand why a quantum computer is not good at it. And it's simple. They can do hard problems with few variables. And logistics is a hard problem with many variables.
Yeah, I mean, in some sense, you can say that Quantum 1.0 was developed mainly through experimentation. There are some simulations. For instance, my old company, we use classical computers to improve Quantum 1.0, but Quantum 2.0 is really to build a computer that can improve the Quantum 1.0. So all these problems which are based on quantum mechanics, we need a computer that can really understand it and on the computer improve all these Quantum 1.0 technologies, which are essential for everyday life.
And perhaps also turn to quantum communication. We talked a bit about the quantum computer, what it utilized from the quantum physics. And as I understand it, Kurt, quantum communication is within the field that you're operating in right now at Sparrow?
Yes, exactly. So as Helmut said, the quantum computer was really one of the first applications was seen to break our current encryption schemes. So this is why, today actually communication on the internet is no longer secure because different governments are storing all data on the internet, because the day we have a powerful quantum computer, then they can crack all the code and read all the things that we are sending around encrypted on the internet. So we need a new way to encrypt things, and we can find new mathematical algorithms, but there are no proof that they cannot be broken on quantum computers. So instead of using mathematical algorithms, people are looking into, can you use physics to break it? Because you cannot break the laws of physics. But there's another application of quantum communication, that is these quantum computers, they need to talk to each other, just like we have the internet, that computers, classical computers, communicate over the internet. But quantum computers, they need to exchange these qubits, so quantum states. So that's another application area in what we call the quantum internet, where you exchange these quantum states between quantum computers.
Yeah, because that's actually the next step built on quantum communication is the quantum internet.
Yeah, and you can do quite interesting things there. Also, for instance, in Denmark, we have a lot of health data. We are not allowed to send them out of the country, but with quantum computers, you can send them out, quantum encoded, and operate on a quantum computer, and send the result back, and nobody can really figure out what are the data, what is the result of the communication, because everything is quantum encoded. So it also gives a new level of security and new possibilities of sharing data without really sharing the data.
There's even crazier things where the classical analog would be what is called homomorphic encryption, where you encrypt two data sets and you manipulate the encrypted data sets. So 2 plus 3 equals 5, encrypted 2 plus encrypted 3 is also encrypted 5. And on a quantum system, using entanglement and communication, you can basically take a data set and manipulate it without actually knowing what the data is. And so imagine, for example, medical records. You could do all these clinical studies without having to worry about privacy laws. You could have, for example, governments do audits on companies without ever getting access to the actual data. That would potentially be possible if we can build this quantum internet.
Let's turn to another word that we hear a lot, is the quantum stack. Because what we have talked about, the qubits and so on here, which perhaps is the sexy part of it, but there is all these parts of the quantum stacks surrounding being able to have sustaining the qubits and so on. What do we mean when you talk about the quantum stack?
It's parallel to a classical computer. You have the processing unit, you have the cooling fan, the memory, operating system, software layer, applications that you run. And in a quantum computer, it's the same. You start with the qubits, and maybe we should talk also briefly about the different types of qubits that we have. Then you have the control electronics. Then you need all this support infrastructure, cooling. Some qubits require very, very cold cooling. Then after that, you have basically an intermediate representation layer where you translate quantum programs into something the qubits can understand, so into pulses. Above that, you would have basically a development kit and then the applications. And so working on all these layers is a monumental effort. And some companies are trying to tackle it end to end. And others, like Sparrow, for example, are focusing on specific components that are needed and that are very difficult to manufacture.
There is a lot of talk in the press where I read about the quantum technology and so on, and there's a lot of hype around it. What is the biggest misconceptions in your opinion?
There is a lot of hype, and I just had to take a quick breath, to prevent myself from saying something. It's unfortunate, with my new VC hat on. It's unfortunate because, for example, generalist investment firms struggle to identify what is real and what is not. And I think the first big misconception is what you can do with these machines. As I said before, they excel at doing quantum-related stuff. But when you look in the press, there are all these claims, we can do machine learning, we can do optimization, we can do quantum simulation. And when you then start looking at it more carefully, you very soon realize that that's not the case. And I can give you a simple example from work that I did before with my team at Amazon. We looked at a optimization algorithm in finance that was supposed to be quadratically faster than the classical counterpart. But when you start with the classical data, you have to convert it into quantum data so that the quantum device can understand it. Then you have to execute the algorithm and then read out the data. At the end of that, you actually had a quadratic slowdown. And so you see, there is in theory, and then there is in practice. And so there is a big gap between what we can do in theory and what we can actually build in practice. And that, I think, is the second large misconception. So not only the application domains, but also what can these machines actually do today is something that we need to be more, we as a whole community, and me as a physicist, need to be more honest about with the rest of society.
Yeah, and I also, when I speak with lay people, they don't really know what is a quantum computer, but they have heard it's something very powerful, so they think it's a really fast machine. So it's not fast. I mean, it's really slow, a quantum computer, but it can work in a different space than a classical computer. So it can work with different concepts, very slowly, but I mean, these states that it work with, they are so huge that they cannot be represented on a classical computer.
So there's been a lot of talk about AI, that if you combine quantum computers with AI, then everything will just go wild.
I think the jury is out as to what impact quantum devices will have to AI. Recall what we talked about earlier, that quantum computers are good at looking at small problems that are very hard to compute. And AI inherently is a problem that requires a lot of data. Having said that, if you have a quantum device producing a quantum data set, and then you run quantum machine learning on the data set, there could be very interesting things that we might be able to do. So working end-to-end in the quantum space. But if you take a classical data set and want to do quantum machine learning, I think this is going to be a very difficult problem to tackle. There's always hybrid solutions, you see, where you can do quantum simulations, to give you an example of a molecule, and then augment the simulations with AI.
Yeah, I mean, we need to think differently with the quantum computers. So we need to develop these new algorithms. But for instance, at Sparrow, I mean, we are involved with a UK company called Orca Computing in making some very simple machines that make new functions that are difficult to calculate on a classical computer. And it turns out that you can put in these functions into your neural networks or your machine learning algorithms, and it will increase the performance. So there might also be some special applications near term where you can enhance machine learning algorithms.
So where do you see the key bottlenecks in this development? You know, if we talk about the entire quantum stack, all layers of the stack, so to speak, at the same level, or something behind and something in the front?
I mean, there are many different modalities, so you cannot come out with a general statement about that. You have to go in and look at each individual modality, and they each have some weaknesses and some strengths. I mean, so if I look into the modality we are working with at Sparrow, photonics, I mean, there the weakness is generating the quantum particles. That's the photons. And this is the problem that we are trying to tackle at Sparrow. Once this is tackled, actually many of the other components have already been developed in the telecom industry, because we have worked with photonics in many years. We have photonic integrated circuits, we have optical fibers, and we also have good detectors. So we believe if we can tackle this problem in Sparrow, then actually we have all the other components available from the current industry.
I have to concur. So there are different modalities of quantum devices. You know, some are based with light, others are superconducting materials, others are individual atoms or ions that are basically free floating in space, held either by electromagnetic fields or optical tweezers. And if I take a step back and look at it with my theorist hat on, I think the biggest struggle right now is error correction. You know, you have to manipulate something, for example, an atom or an ion, if it's that type of computer, and make it do certain things, but you don't want to influence it, because otherwise you decohere it, you collapse the wave function, and your computer is broken. And so you have this horrible challenge of trying to manipulate something without actually influencing it in some ways. That is very difficult. Now, obviously, you have to somehow manipulate it, and that causes noise. It can be environmental noise, like thermal noise, you know, it can be electronics noise, etc. And because of that, and because quantum mechanics is probabilistic, these devices produce errors, far more errors than a classical computer. And so we need to come up with error correction schemes. Now, there is one other fun fact about quantum we didn't talk about, and that is the so-called no-cloning theorem. You cannot copy quantum information. So you cannot do, like in classical computers, where you do a simple parity check, where you say, okay, one classical bit is going to be 3 physical bits, and if 2 out of 3 are 1, then it's probably a 1. And if 2 out of 3 are 0, it's a 0. In this case, you cannot copy the data to 3 bits. So you have to come up with far more clever error correction schemes that are much more involved. And I think this year, 2025, and it's great that it's 100 years quantum, is the first time that we have had the first error correction demonstrations where the amount of errors of a logical quantum bit made out of several physical quantum bits was lower than the actual errors in the counterparts. So that is a big struggle, correcting these errors. Once we've figured that out, we can build, putting in layman's terms, error-free computers that allow us then to do the algorithms that we want to do, like simulating chemicals.
You mentioned that there are a lot of, competing technologies or, trying to obtain the same solution by different approaches. Will there be one technology that will be superior to all the others, one winner takes it all, or will it just be, that approach will be the right one for this problem, or how do you see that?
I mean, it's clear photonics will be the winner, so it will outcompete all the other technologies. That's my clear thinking. But I mean, I think also the next 10 years there will be many different contenders. At this point in time, some are further ahead, but difficult to scale. Photonics right now is a kind of a dark horse. I mean, so it's clear that photonics is very scalable, but we need to demonstrate the early operations. I mean, so some have been demonstrated, but we are behind some of the other modalities at the moment.
Talk a little bit about what Sparrow actually does.
Yeah, so Sparrow is based on the research of Peter Lodal at the Niels Bohr Institute, and what he have put his mind around for the past 20 years is how do you create light, and can you control light down to the single photon? And what he have done research in is what's called quantum dots. It's a kind of artificial atoms where you put together a bunch of gallium arsenide atoms into a small pyramid such that it has discrete energy levels, just like a single atom. So this is why we call it an artificial atom. And can you now control the emission of light from this quantum dot and catch the light with very high probability? So then you put it into nanoscale or microscale structures called photonic crystals, such that you can control the light emission and catch the photon. So this is a so-called deterministic single photon emitter. All quantum computers need quantum particles, and the quantum particle of light is a photon. So it's the lowest constituent of light. So a light wave consists of many different photons. So to do computations, you need to control the light down at this quantum level, which is the photon. And you need, photons are very nice because they don't interact very much. So I mean, this thing about disturbing the quantum system is actually difficult for photons. I mean, they're not easily disturbed. So one of the challenges is how do you actually manipulate these photons? But I mean, now there are schemes how to manipulate different photons, and Peter have also come out with a blueprint of how can you make a fault-tolerant quantum computer, and this is what we are working on in Sparrow to make this critical component generating these photons, which can then be manipulated and measured and provide a photonic quantum computing system.
Sparrow just raised, as you said in the beginning of this talk, 27.5 million euro in a Series A funding round, which is Scandinavia's largest quantum technology investment, as I understand it. Why is right now the right moment for making such a huge investment in Sparrow? And will it be enough for your continued journey?
No, it's never enough. I mean, quantum and quantum hardware is really, really expensive to develop, but also the potential is really, really big. I mean, as Helmut said, NVIDIA was developed chips for GPUs 20 years back, but now it's a modality that is used everywhere, and it's really essential for the world and developing technology. And quantum could be the same, and Sparrow could be one of these defining companies being the winner in this race. So this is why you should invest. And also Europe. I mean, in Europe we are behind in all aspects. I mean, we didn't win the semiconductor race. We didn't win the AI race. In quantum, we have some really, really strong scientific groups, like Peter Lodal. I mean, his group is one of the world leading in this field. So if we want to be part of the quantum race, I mean, we need to invest in Europe. That's clear.
So we have the technology, but the funding is an issue for Europe. Is that right, as compared to the US, for instance?
We have the knowledge and we have the potential, but it's really expensive to develop this type of technology. So this is why we need investments. We need new funds like the one Helmut has started. But it's also clear, I mean, VC funds cannot do it alone. I mean, we need to create a market also in Europe. Just like in the UK, there's this NQCC testbed where we have delivered a system. So investors need to see that there's a market evolving, and that there's a way that they can get back the money at some point in time.
And that could be a nice transition to go to you, Helmut. You are at the 55 North Venture Quantum Technology Fund, the largest in the world right now.
Right now, yes.
But could you briefly perhaps talk a bit into, you have already made some investments in some portfolio companies. If you can talk a little bit about that and what kind of technologies they are developing
So first I'd like to follow up on what you said. I fully agree. You know, in Europe, education is universally available. There are phenomenal universities, stellar research teams, but then there's a gap in the funding missing to take these ideas from the lab into products. And so if I look at the whole world right now, I think Denmark has probably the best thought out quantum roadmap that I've seen as a country. There are very clear milestones that have been made, from building the infrastructure, for example, the quantum foundry, to supporting research teams to build incubators and communities. And now in this final step, they launched 55 North, which is co-funded by Novo Holdings and IFO, such that there is enough funding from VC for quantum technologies, not only in Denmark, but also in Europe and the rest of the world. And so it's really this type of support that is needed to take these experiments and make them into devices. 55 North, as my colleagues told you in the last episode, was launched a couple of months ago. It's 3 partners. We have now new heads of operations that we recently welcomed to the team. And I think our advantage over other more generalist VCs is that the 3 of us are technically quite deep in our own fields. And that allows us not only to assess the technologies, but also down the road provide the necessary support to the founders. We are able to speak their language, but we're also able to support on the business side of things. And so this is why 55 North was created.
And what kind of businesses have you specifically invested in?
So we have already done 2 investments. One of them is in a full stack quantum computing company out of Finland called IQM. They are definitely the leaders in quantum technologies in Europe for full stack systems, meaning that they work from the qubits all the way to the software layer. They have sold several machines to date. They're both available in the cloud as well as on premises, so you can actually buy one and put it in your basement. I don't know why you would do this, but if you're so inclined. And so we felt that it would be a good idea to support them in their latest round. We have also invested into a company out of Germany called Qtra. Qtra builds specialized refrigeration units. As we said earlier, these systems are very delicate. They need to be cooled down to extremely low temperatures. And the way this is traditionally done is with so-called dilution refrigerators, where you have a mixture of helium-3 and helium-4 isotopes. Helium-3 is a very scarce resource on the planet. You can only generate it in nuclear reactors and fusion reactors. So it's not something that you can just dig out of the ground easily and use. And so we will need a lot of helium-3 coming down the road. So coming up with alternate technologies that do not rely on this, like the devices Qtra builds that focus on a magnetic effect that allows you to cool down things, is going to be very important down the road. Not only that, they have a very clever sample loading technique. Today, if you want to take something out of the refrigerator on a quantum device, it can take days for you to heat it up, pull the thing out and put it down. With a Qtra device, it's basically almost like pulling a beer. You know, you just hold a lever, you pull the sample out, you put the sample back in. It takes only a couple of hours versus days. And so characterization of devices at low temperatures is much, much faster thanks to their technology.
May I come with a recommendation for you, Helmut? You should save a little for our CSB round. You would regret if you're not part of that.
We still have some in the coffers.
Perhaps as an outro, when we've heard a lot about this and its potential, and also importantly, I guess, where it cannot be utilized, where do you see, how does all this impact, or how will all this impact on everyday life?
The pace of new development in IT, in pharma, and so on is fast today, but with a quantum computer, it would speed it up tremendously. So I think the normal citizen will not see it as new compute power, but they will see it in what it enables. For instance, drugs, it goes really slow. Take Novo Nordisk. So maybe there's a new drug every second year that they can put on the market with kind of this improved simulation capabilities. The rate of progress will be on a different scale, simply. So the new drugs will come to market much, much faster.
Yeah, I concur.
Yeah.
It's not going to be, there will not be the quantum phone anytime soon. But the same way that today, we have supercomputers that live in data centers that none of us really ever get to see, quantum devices will also live in some sort of data center and provide compute capabilities for some of the world's most challenging problems. And so I also look forward to a future where we'll have better chemicals, less pollutants, better medications, vehicles that can drive thousands of kilometers on one battery charge. That would be phenomenal.
So where do you see the next big breakthrough within this field?
Within the photonics, there's the US company PsiQuantum, and they are going to build a photonic quantum computer in Brisbane, Australia, and Chicago. It's going to be ready in 2027. And what, at least I have heard some rumors about this device will be orders of magnitude more potent than what we have seen today. So it would really put photonics as a forerunner in quantum computing if they can deliver just part of what they are promising.
the next breakthrough that is happening or starting is going to be error correction. Once we can stabilize these qubits and make them less error prone in any of the technologies for that matter, because there's different modalities, that's when we'll be able to really put a focus on developing further software stack and look deeper into applications. And I can't wait for the day that programming a quantum computer will be as easy as programming a classical computer, because then all developers out there that are massively creative people will just sit down and program something up and say, hey, look, I found a new way of doing blah. Whereas blah is something we never even thought a quantum computer could do.
Thank you very much. I'm looking forward to see what kind of new investments you are making in 55 North.
Yes, there's some coming.
Your continued journey is Sparrow. Thank you very much for enlightening us all. Thank you.
Denne podcast er produceret af Mazanti-Andersen advokatpartnerselskab. Du kan holde dig opdateret på markedstendenser og juridiske nyheder på mazantipulse.dk.